Bojańczyk from the University of Warsaw. We'll be talking about infinite sets.
Thank you. I'm a cheap speaker, you know. So hello. In this lecture, I'd like to talk about algorithms which operate on infinite sets, but they're not really infinite. They're just, well, you see how infinite they are. Okay, so the idea is to find some kind of infinite sets which are finite enough to be operated on, and to write programs which operate on them. So I will start today. I will give you mainly examples to motivate the abstract definitions that will follow later on in the lecture. So let me start with the following example. You are, big font. You are given vectors so these are vectors over the two-element field. You say to choose some infinite dimensional space. Maybe this. This is too much, but you have a suitably high dimensional vector space over the two-element field. So we're given several vectors, and we want to know if they're linearly independent. So if this is the two-element field, there's no need for coefficients because coefficients are 0 or 1. So the question is, can you find a zero? Can you sum some of them and get 0? This is, technically speaking, this is not a property of the set, because if you have a repetition, for example, then they're linearly dependent, okay? In the sense. So this is your problem. And we want this to be done, and this is the reason you might ask, why did I draw the boxes? Well, you should think of it as the input to a Turing machine. So each vector is in a single cell, which means that we have like an atomic data type of vectors, and you can put such a vector in a single cell of the Turing machine. Okay? So this type of idea of having these atomic data types is the general theme of this lecture. So we want this to be done by a Turing machine. And what can the Turing machine do? This is meant to be an example, so I won't be very specific, but let me write it like this. It has registers, and then it can do addition on these registers, and maybe it can do conditionals. It can ask, is this register equal to that register, and based on the answer, do something or something else, okay? So you could probably come up with a Turing machine which has registers and think of a notion, and you have the correct idea, okay? Now, one theorem, and I intend to prove this theorem towards the end, once all of the definitions are in place, is that it cannot be done in deterministic polynomial time. Okay? So there's two obvious ways to do this. None of them are deterministic polynomial. The first one is that you try out all subsets, and for each one you try to check if it leads to linear dependence. And this is deterministic but exponential time. And then the other one is that you try to do it, just guess the subset left to right, and this is linear non-deterministic time. And it turns out you cannot do this in deterministic polynomial time. Clearly, it is important here our machine model. Okay? Because in general, if you're given like the vectors in the usual sense as a sequence of zeros and ones, then you could do all sorts of things like Gaussian elimination, and then you could solve the problem. So the result is not going to be about the fundamental problem of testing dependence or independence in a vector space. It is going to be more about the way these machines can access their data. Okay? So I want to make this clear because I'm going to give theorems like P is not equal to NP and stuff like that. This is not meant to be the actual P equals NP. It's more about the way these machines access their data. Okay? So this is one thing that we're going to see. Let's continue with this example, and we can have it as let's look at the non-deterministic left to right procedure. This you can think of it as actually a finite automaton. In the same sense this was called a Turing machine, then you can think about a finite automaton also with registers and things like that. So let me just draw it and you can figure out what it's going to be. You start, and the idea is that apart from control states you have registers. Later on these registers will be formalized in some kind of way, but I hope that the word is kind of intuitive enough. And what you can do is, if you read a vector, an input letter V, you can, so this is what you read and this is what you do. You can do, here you do nothing with your register. Or you could put it into your register. Once you're here, so at some point you load the first vector into your register, and then sometimes you add the input vector to your register, sometimes you don't. Okay? And then when do you accept if your register is 0? This additional state, it forces us to use a non-empty set. Okay? So this is a non-deterministic finite automaton with registers. The input letters are these vectors, and it's allowed to do some things on the vectors, namely add them to each other and test them for being 0. Okay? That's an example of a register automaton. Okay. Let me give here another example. Here it was about vectors, so now I will downgrade to a simpler example. So on this whiteboard, a blackboard, we were dealing with data which was a vector space, and you could have a binary addition operation and maybe constant for 0. The constant for 0 is not really needed because you take any vector and you take x plus x and it's 0, so it's not really a big deal. But just this was the structure that we dealt with. So we had Turing machines which would store these things in registers, and then they could operate it along with the structure. We could also have finite automata which did things like that. And you can imagine this definition for any kind of structure. Structure in the sense of logic. So there's a universe and there's some operations on it and maybe some relations on it. Okay? What could be the simplest possible structure that you could have is this one. Some infinite set, I don't know, I'll call it V as well. And what are the relations and functions on it? There are none. So I will write equality Because in logic, in the type of logic that I discuss here, equality is always there. So just so that I don't have to write an empty list. Okay? And underline the fact that equality is always assumed to be given. So suppose we have a structure like this, and you could also talk about Turing machines. And you could maybe ask, for example, you're given as an input a list of these atoms. I call them atoms. I start to call them atoms. And then the question is, or the output, is there one that appears twice? At least twice. So now you can quickly come up with a Turing machine which does this. It sort of picks up V1, loads it into the register of the Turing machine, scans it, and if it sees V1 again, then it accepts. Otherwise, it eliminates V1 and it does the same thing for V2 and does this in Turing machine quadratic time. Okay? You could also try to think of a finite automaton in the same sense as here, which does this, and it would do the obvious thing. It would be non-deterministic. So at some point, when reading some V, it would load it into its register. So for some time, it just reads V and does nothing. So there's no actions performed. This is not the same V. This describes a transition which reads some V and does nothing. Doesn't have to be the same V. And then once it has loaded it into the register, let me write W just to underline that it doesn't have to be the same V. And then at some point, if it reads V, and a guard of the transition is that it's equal to the register, then it accepts, and this is an accepting state. And it stays here forever. Okay? So not a very obvious automaton which just checks that something appeared twice. It's a non-deterministic automaton. Can you do the complement? So, what do you think? I mean, some of you know, but if you don't know, if you didn't know today, then and you know now, tell me. Can you do the complement? So, something that does not appear, nothing appears twice, which means everything appears one time. Well, probably I wouldn't ask the answer is no, you cannot. And here's a sort of argument. It's not a real argument, but it's an intuition. Imagine you could do the complement with a non-deterministic automaton, which means that there's a non-deterministic automaton which checks that every letter appears once. And say this automaton has 12 registers. Okay, and it has to have 3 registers. Okay? And then you run this hypothetical automaton on the input 1, 2, 3, 4, 5, 6. These are all different data values. So it should accept. So it should have an accepting run, and then you look at this accepting run, and then you ask, what is the state here? In this state, where it's going to be something like one of these things, and let's call it Q, and it's going to have some register valuation, 2, 3, 1, or maybe 4. Because it has 3 registers, then necessarily we needed to forget something. In this particular case, it forgot 1. Okay? So then what you're going to do is you're going to write here 1. So you're going to, do a different thing. You're going to change this with a 6. Now, the 1 would be kind of the same anyway, so instead of forgetting 1, it would forget 6. This all would require some justification, which will be presented later on. For now, it's just intuitive. if on 1, 2, 3, 4 it ends up here, then on 6, 2, 3, 4 it should also end up here. Because the only thing it can do is check equality. So how can it be sensitive to the fact that it's 1 and not 6? Okay?
But it's one of the possible states.
Yes, it's one of the possible states, but nonetheless, this run continued to accept. So now so if you have these two possible inputs, let me put like this. This was the one run which accepted. Now, there is a similar run here, which ends up in Q2, 3, 4. Okay? And now you combine this run with this run, and you get acceptance. Now, this would need some formalization. In particular, I would need to tell you what the model is, but I hope that any intuitive idea of registers would be consistent with this argument, and I will give you a precise model later. So what is the situation? What we have here is we start with some kind of data that we're allowed to operate on. We model it as a structure. It's typically infinite. So here there's infinite many data values equipped with equality. Here there's infinite many, an infinite dimensional vector space over the two-element field. We specify at the beginning what we're allowed to do with these data values, so maybe add them or just test for equality, and you could imagine other things. And then based on that, we build a Turing machine, a finite automaton, but we could also build context-free grammars, and so on. Okay? And then study their properties. So let me write this as a plan. The plan is as follows. One, we start with a structure for the data. And the structure is a structure in the sense of logic. So examples we could have are, say, the natural numbers with equality. It's any countable infinite set with equality. It has only equality. It doesn't matter if it's the natural numbers or anything else. Okay, so this is the example here. Or you could start maybe with this vector space with addition. So some maybe counted infinitely dimensional vector space over the two-element field with addition. Or you could start with the integers, the group of integers. Or you could start with the multiplicative group of integers. These structures, this one I didn't say exactly what vector space, but this will be explained later on. They all have names. Who knows the name of this one? Well, you could call it the group, or the additive group of integers. But if you think about it from the perspective of logic, meaning, for example, you want to write formulas on top of this structure, which quantify over elements and add them, then from the perspective of logic, this structure has a name, and it's called Pressburger arithmetic. Sorry?
Don't you need inequality?
I will get this. So you would need positivity. So if you, and I guess this is what you meant. So here, if you use it the way I defined it here, if you swap +1 with -1, then it's an automorphism. So there's no way in first order logic to tell if you're a positive number. Okay? So then you can add this in several different ways. You can add this, but the natural way is to just add an order. Okay? Okay, this one is called Skolem arithmetic. And the reason why they have these names is that the people with these names, they proved that, Pressburger proved here in Warsaw that if you take a formula, for example, this norm formula says that for every number, if I add this order here, there exists a bigger, it's not a very fancy property, okay? There exists a bigger even number, or there exists a bigger number. Huh? It's a typical formula you could write. You could write something slightly more fancy which says that for every number there's a bigger odd number and stuff like that. And what Presburger showed is that any formula you write, there's an algorithm which tells you that formula is true or false. Okay? And some other stuff related to that. That's why it has a name. Another structure, which is kind of maybe famous, is this one. So this one is called Presburger arithmetic, and this one is just called arithmetic. Okay? And it's more famous but less useful in this context because it's undecidable in the sense that you don't have this property of Presburger, that given a first order formula you can decide if it's true. In fact, there's very simple formulas which are undecidable. If you don't know this, I tell you because it's, you surely have heard of it at some point. If you have even a polynomial, formulas of this form, so purely existential. And so, can you find integers xy which make this polynomial 0? This is known as Hilbert's 10th problem, and it's undecidable. So it's kind of, that's all, so how undecidable it is. So you could think about Turing machines where the data values are from Presburger arithmetic. So your data values are integers, you get to add them to each other, maybe compare them for order. Or you could think about finite automata where the data which operate on Presburger arithmetic, and likewise for the other structures. And I'll try to discuss in this lecture what happens here. Let me give you maybe 2 or 3 more nice examples that will be used in the lecture. You could take a graph. So this is in terms of a directed graph. In the terms of logic, this is just a structure with a single binary relation. It's a directed graph, so it's just the same thing as a directed graph. And so for some directed graphs you get interesting things, so for some directed graphs you get less interesting things. You can clearly come up with complicated infinite directed graphs. But there's a very nice directed graph where you get interesting things, and it's non-trivial. It's called the random graph. The random graph, which is kind of, it's not a random graph, but it's the random graph. So who's heard of the random graph? Hands up. Okay, so there's one random graph. Okay, and it will turn out that this theory works for everything that I will discuss. The random graph is a perfect place to do it. So it will turn out that finite automata running over the random graph are a very natural object, and they have good decidability properties. Another thing you could do, you could take the ordered rational numbers. Now, like there's many so in the same sense as there's many directed graphs, and the random graph will turn out to be the best one for our purposes. In the same way, there's many total orders, like the natural numbers, or omega, or omega squared, or the integers, and it will turn out that the rational numbers are the good one, and I will explain when it's good. Okay, so you can come up with all sorts of start with all sorts of structures. That's the data, and step 3 is define Turing machines, automata, grammars. You can see my background is in automata theory, but we could also do things. Yes?
Is there step 2?
Thank you. I was wondering why my steps are wrong. But you can also do things that do not come from automata theory. I have to look at my notes to find something that's not from automata theory. But let's say, for example, you might want to study three-colorability of graphs. I will explain what that means, in this context. Etc. And step 3 is write papers about. Okay, so that's the program. We've been doing this for 10 years. Now, what I tried to convince you is that it's not as bad as that. Okay? In the sense, there are some quite general results which work well. You don't need to write a new paper for every combination of structure and problem. Okay, there are some commonalities. And the nice thing about them is that, for example, there are good structures here, and I will maybe underline the good ones. Well, it's easy. These will turn out to be good, the others will be bad. That if you start with a good structure, then there's uniform results which say that everything that's true in the usual sense is true here as well, stuff like that. Okay? So maybe let me begin today's lecture. Well, today's lecture will be about at least one improvement on this stupid program here, which is that at least you don't need to define all of these things in each case. There's a uniform definition. Okay? So there's a uniform definition of Turing machine and everything over this, and you don't even need to remember what a Turing machine is. So the idea is as follows. My purpose is to use colors intensively so that you are puzzling why did I use blue, and there's actually no reason for that. Okay? So the idea is, instead of for every data structure like this, defining what a Turing machine and so on, we only need to define for every data structure one thing, namely what is a finite set. So actually the real step 2 is define finite sets. Over a structure A. A is one of these structures. Okay? Once we have defined what it is to be a finite set and subject to reasonable assumptions about what a finite set is, then a Turing machine, well, maybe let me say a finite automaton, or a graph I guess it's easiest, is a pair of finite sets such that one is a binary relation on the other. Okay? So what we need for this program to work is, given a structure A, so this is a set equipped with functions and relations, so like these things, so it's a structure in the sense of logic, okay, in the sense of model theory. We want to define finite sets. I will give you a definition. In fact, I will give you two definitions, which will sometimes be equivalent, sometimes not. And what properties should this have? The number one, how do I number these properties? Yeah, well, first of all, it should be kind of interesting. So an obvious way would be to just say, it's the usual notion of finite sets, and we're done, okay? Clearly this is not what we want to be. So we wanted to capture, contain, well, generalize the usual finite sets. So the finite sets in this quote. So every finite set in the usual sense should also be finite, but there should be more examples. So for example, I don't know, the entire universe of the structure should be a finite set. That's one thing we would like to have. Okay? So for example, if your data structure is this, then the entire set of rational numbers is a finite set. Okay? So you're going to be, and if for example you end up, say, so this is going to be a legitimate input alphabet for an automaton. A legitimate input alphabet will be a finite set. So the set of all rational numbers will be a legitimate input alphabet. You're going to have finite automata which input rational numbers. Or, this is kind of more interesting, there will be, I'm not sure I will have time in the lecture to do this, but there will be a programming language, and the programming language will store these quote finite sets in the variables. So at some point the program will store the set of rational numbers in its variables, and it will be allowed to do a loop over all elements of a set stored in a variable. So it will be allowed, there will be a program which will do a loop over all rational numbers. Now, of course, this leads to the question, I mean, what does this exactly mean? And if there will be time, but I don't think there will be, I will try to explain what that means. It should have, I mean, reasonable closure properties. Like, I don't know, if this is a finite set and this is a finite set, then you should be able to take the pairs. Or maybe, well, at least this. Take a union of two finite sets, that should be fine. Yeah? Or maybe this. A subset of a finite set should be finite. Well, this is actually questionable, and I will explain that in a moment. And another thing you might want, well, not might want, but this is like the entire point of it, they should be algorithmic. So you can represent a finite set so that you can input it with an algorithm and then run algorithms on them. So they should have finite representations and algorithms. So you should be able to represent every finite set in this quote finite set in a finite way. Okay? Now already these three items are inconsistent. Why? Because let's say that this is our data values. Well, in fact, any infinite set. This one, for example. You want the set of all data values to be finite. You want every subset of it to be finite, and you want them to be finitely representable. Well, that cannot happen because there's uncountably many subsets you could choose, so there's no way of representing them. Okay? So it will turn out that we need to do a little bit of work, but this is going to be well-behaved subsets or something. There will be a notion of well-behaved subsets. Okay? So the program is as follows. We're going to now do this in a moment. I'm going to define a notion of these finite sets. Once you have the notion of finite sets, you immediately get what does it mean to be a Turing machine, you immediately get what does it mean to be a finite automaton, what does it mean to be a grammar, or for example, what does it mean to be a graph. It's just going to be a graph so that both the vertices and the edges can be represented in a finite way, and by as item 3 that they can be represented, it is a meaningful question to come with a graph and ask, is it free colorable? And you could just ask, is this decidable? And to be honest, I don't remember if it's decidable. For specifically free colorability, I think it is, but I'm not sure. Okay. So let me maybe start with defining what a finite set is. And there are two approaches to this problem. There's going to be two notions of finiteness. There will be the first notion, it will be, I will explain, this is what I'll do today, set builder expressions. And the notion B will be orbit finite sets. It will turn out that for the good structures, these are the same. This will require some proof. But in general, they are different. In fact, the orbit finite sets are only meaningful in the good structures. So in that sense, whenever they are meaningful, then they're equivalent to these set builder expressions. But there will be profit from having two different definitions, and the reason is going to be that this one is a very syntactic notion. So it's just, if you don't like logic people, then you expect them to write this type of thing that I will write in a moment. The second one will be much more semantic. It will be, there will not be any syntax attached. But because it's equivalent, there will be theorems where both representations are used. So you can do some things because of representation A and some things because of representation B, and you get the job done because both of them are equivalent. So let me start with this set builder expression. So it's a very simple idea. So what is set builder expression? I mean, it's like, you don't know that you speak in prose. So you've written it many times, but it's just you don't know that it's called like that. It's something like this. Say, let's assume that the data structure is this. And then a typical one is going to be 5. 5 as an element of this. This is going to be okay. Another one is going to be, you can nest these things. But then you can take infinite sets. So you can take, for example, all x's, which are, well, I will write it parametrically. So this is the structure A. And the underlying structure, I will call it the atoms. So this definition is parameterized by a structure, which I will call the atoms. So the atoms have a set and some operations you can do on it. So you take the set of all atoms such that x is not equal to 5. So all atoms except for 5. And of course you can write here such that true, and then you get the set of all atoms. Or you can maybe nest these things. You can go all atoms such that x is not equal to y, and then y is for all atoms such that y is not equal to 3. So you get all subsets of the family of all subsets of the atoms, which misses at most one exactly one atom, and that the atom you miss is not supposed to be 3. Okay? So the idea is you just write any expression like this. This is a set builder expression. Okay? I will give you a slightly formal definition, but there's really nothing to it. So what is the syntax of a set builder expression? These are all, I want to define it by induction. Don't worry, it won't take too much time. I want to define it by induction, And I will need to introduce free variables because although the entire expression, it describes a set, it doesn't depend on anything, but it's constructed compositionally from sub-expressions. And a sub-expression such that this one here, it has a free variable x. So depending on x, it gives you a different set. Okay? So generally speaking, a set builder expression, it will have some free variables. In the end, we're interested in set builder expressions which have no free variables, and then they just denote a set. But along the way, we'll have to introduce free variables. So it's just what you would expect. You write a simpler set builder expression, but you're allowed to add these new variables. So you're allowed to go, you create some new variables, and then you say, for all, for yk in atoms, so these variables, they range over the atoms, and then there's some condition, such that, and you write a condition, and this condition is in first order logic. So you're allowed to quantify things. Okay? Is it clear? So that's how you construct set builder expressions. You also need union. So if you have already constructed several set builder expressions, you can construct their union. Okay? So this finishes so beta here is an already constructed set builder expression or possibly a variable. So that finishes the syntax of set builder expressions. And you can see that all of these are examples where, formally speaking, some of these are syntactic sugar. So let me maybe stay with this. Let me maybe analyze one of them. Technically speaking, 5 is just all atoms x, such that x is an atom, such that x equals 5. Yeah? And for similar reasons, these what is this? Well, this is the union of two sets, one of which is the singleton union 1, and then you can describe these in some way using these.
Shouldn't it be x in A, not in
It should be, yes. Well, so this syntax is quite flexible, and it also, one of the things it does is that this is not surprising because this is sort of the way it was designed 100 years ago. The language of set theory is rich enough to capture all sorts of data structures that you might want to do. For example, trees. I mean, a tree is very naturally can be modeled as a set of sets of sets of sets of sets, yes? Like the two children, a set is nothing but a tree, yes? Well, actually, a set is more like an acyclic graph, where the edge relation is elements. Because you might have shared, you might have, say, a set, and it might have two elements, and these two elements, they share a common element, and so on. So it's an acyclic graph. Which is kind of funny, because in this, from this perspective, if you think about set theory, it's just about a single graph, meaning the vertices are sets, and the edge relation, directed edge relation is an acyclic graph, and the directed edge relation is just the element relation. So, all of mathematics is just the study of this one infinite graph, but it's maybe not very useful as an observation. Okay, so I want to, I guess I should be finishing in 10 minutes, but it's going to be good. So using this basic syntax, you can get all sorts of data structures, and at some point I will just assume that I'm not going to be describing pedantically how everything is written as an expression, but I'll just do that. But let's do some examples before we do that. So for example, why is this? Well, this one we've already done. This you can write as a set builder expression. I should write such that true, but I won't do that. What about this? Well, let me write the obvious thing, and you'll see that there's a small issue there. It's not very important. Such that's true. Well, the issue is that these round brackets are not part of the syntax. But this is not a big issue because there's a way to define it, namely this is called Kuratowski encoding, and if you've it's a classical exercise that once you know this set, you can recover the first and second coordinates, so it's a pair. So you don't really need pairs as a basic thing, and it's true for all kind of data structures that you might be using. So sets it's a minimal syntax, but it's good enough for everything.
Can we just do the second part, just the set of this? Why?
No, because here you don't know which is the first coordinate and which is the second coordinate. So this is like an unordered pair. So unordered pairs are more general than ordered pairs is the slogan. But in fact, it's like more general than every other data structure, which requires some justification, but we won't do that. Okay? And let me maybe give you another one. You can also do functions. So for example, the projection function. It's what? It's if you just if you remember the unfoldings of your definition, it's the set of pairs x, y, x ranging over all atoms. Now what you would need to do is you would need to write an expression beta x of y, which gets two atoms and produces this, but this is just fiddling with these sets, it's not a big deal. So you can write functions, because functions are special cases of sets of pairs, and you can write some sets of pairs, okay? So now we can revisit this, and this is actually, this finishes the definition of the first one, set builder expression. So the first approach is to say that the finite sets over A are those which can be described by set builder expressions. Okay? This clearly generalizes every finite set because, well, here. You can do union because it's just built into the syntax. You can do products. It's this type of thing we can do during the exercise session if you want. You can't do all subsets because, as I mentioned, you can't do them anyway. But there's going to be certain, we will identify later on what are the types of subsets you're allowed to take. They have finite representations. Well, it's sort of like I just define them by, it's whatever you get out of this finite representation, so they have them. And as it will turn out, there are certain algorithms. So what kind of algorithms do you want? And I think I will finish with this question. So it's going to be as fun. What algorithm do we potentially want? So here's one. I get two sets, and I want to know if they're equal. And that should be something I can do. And well, can you do it? Can you not? It's not completely clear. It will turn out that you can do it if your structure has a decidable first order theory. But this is not entirely obvious. It's actually symbol pushing, but it's not entirely obvious because this is like a set of sets of sets of sets of sets, and this is a set of sets of sets of sets, and then they could align in various different ways, and you need to figure that out. But it will turn out that this is going to be decidable if the underlying structure has a decidable first order theory. So given a first order formula, you can decide if it's true or false. So in particular, it will be true for almost all of these, including Pressburger and Skolem, because these are well known for having a decidable first order theory, but in arithmetic it's not going to be true. And you can kind of quite easily see it because you can, for example, with Diophantine equations, this Hilbert-Senf problem, you can easily write an expression which describes to you all solutions, all roots of a polynomial, and then you can just ask, is that set equal to an empty set or not? Okay? So this will turn out to be fine under this basic assumption which you need anyway if you want to operate the first order logic. But there's other more fancy questions. Maybe we'll finish with this one. We're given a graph. What does that mean? There's two ways to view it. It's they're the same. The first one is that we're given two sets, V and E, and it so happens that E is a set of pairs from V. Okay? And both V and E are given by set builder expressions. And then, what's the output? Here you can take any graph question, like, is it connected? Okay. Another view doesn't make too much of a difference. G itself is a pair. So a pair of sets is a set, because everything is a set. So you're just given G. It's not an important thing, but I just want to say this representation is good enough to support pairing and all sorts of data structures. So you're just given G as a set builder expression. But the fundamental question remains, how do you decide if it's connected? Okay? Now this is far less clear than the first question. In the first question, we will see this maybe even in the exercise session. It's really just pushing around first order formulas. And the second question is far from clear. And in fact, in the bad structures, so in the good structures, it's going to be decidable. But this will require some, I think, interesting argument. And in the bad structures, even decidable ones like Pressburger arithmetic and Skolem arithmetic, this problem is going to be undecidable. And in order to deal with problems such as this one, it is going to be, well, we are going to use this semantic characterization of orbit finiteness, which is defined in terms of groups. Okay. So I think I will just maybe a few sentences to. Is it done now? It's like 1 hour, yeah? Or am I wrong?
Hour and a half.
It's 1 hour and a half. Okay. Well, so I'm not wrapping up now. I'm going to continue then. That was unexpected. So just a slight wrap up and then I'll improvise. It's not a big deal. It will be okay. So what we have now is a notion of a finite set. It means you can write it down in this particular discipline. Okay? It's kind of robust and it can do it can cover quite a lot of interesting examples, and I will show you maybe 1 or 2 examples in a moment, and maybe more in the exercise session. And then my point is to discuss algorithms such as this. Okay, so let me start off with an example of why it's not completely obvious. So let's take the connectivity problem. Okay? So suppose before I do that, is it clear now what a Turing machine is? It's a Turing machine where the states are described by a set builder expression. The word alphabet is described by a set builder expression. The transition function, which I don't remember, it like inputs 3 arguments and outputs 2 arguments, whatever it is that it does, is described by a set builder expression. The set of accepting states is described by a set builder expression, so on. Okay? So there's a meaningful notion of a set builder expression Turing machine, and this gives a precise meaning to the questions that I asked at the beginning. So suppose that you have this vector space and you're allowed to use Turing machines where everything is defined by a set builder expression, and can you solve linear independence in deterministic polynomial time by such Turing machines? And the answer will be no. But this will require some proof, and this is what we're going to do at the end. In 4 lectures, at the end of this lecture, the 4th lecture, I think. I said registers, if you remember. Yeah? Why did I say that? Well, it was just to give you intuition, but so far what we can see from these examples, this is a finite set. So it's a legitimate choice for the state space of a Turing machine. So at least you're going to, one of the things you're going to be able to do is in the state of the Turing machine to store 2 vectors. That's why I said registers. But there's going to be all sorts of strange things that you can have as well. Let me give you one example. Suppose that the atoms are have just equality. And consider the following set. It's going to be for all x, y, z's. Subject to no conditions, and it's going to be what is this? What is this set? Well, in the sense that there's 3 things, but it's triangles modulo rotations. Okay? So it's not the set of all triples of atoms, but it's the set of all triples where you identify 2 triples if they're equal modulo cyclic shift. Okay? So it's triples modulo cyclic shift. This is a legitimate set. So when we are proving that something cannot be done by a Turing machine or by a finite automaton, we will also have to take into account finite automata where the state space is like this. And you can come up with some mind-bending things. And maybe let me give you another one, which is this. It's also with equality only. I don't remember if it's this one or a similar one. Maybe A, B. These are unordered pairs, yes, and triples. It turns out that if you consider Turing machines with this input alphabet, okay, then non-deterministic Turing machines and deterministic Turing machines do not have the same expressive power. which is crazy. So usually, if you have a non-deterministic Turing machine, then you can determinize it. I mean, it's going to be much slower, but it's going to give you the same yes/no answers. You essentially just browse through the tree of possible computations of your non-deterministic Turing machine and you search it breadth first search. Slow, but gives the same answer in the end. This will not work for Turing machines in this infinite set, but this is going to be one of the simplest examples of an alphabet where this happens. So these sets can be kind of strange. Okay. But let me continue.
What's the signature for this?
Equality only. Okay. Good. So let me now give you an example of what happens with, say, problems that you get with Pressburger arithmetic. Consider the following graph. The vertices are going to be pairs of natural numbers. You can clearly easily get the pair of natural numbers here as a set. Yes, it's all pairs of numbers x, y such that both x and y are greater than 0. Okay? And for example, what is their edges? It is going to be over x, y, right? So there's a directed edge from this pair of natural numbers to this pair of natural numbers if such that if x is equal to 0, then y prime is equal to y plus 1 and x prime is equal to 0, else y prime is equal to y minus 1, x prime is equal to x plus 1. Something like this. This is clearly definable, yes? It's a first order property, it's quantifier free about these four numbers x, y, x prime, y prime. Okay? What does this remind you of? What kind of undecidable entity does this thing remind you of? A two-counter machine, a Minsky machine. So what's a Minsky machine? If you remember, it's a device which has a finite state space and it has two counters. Well, duh. And the way it works is if it's in a state and it reads an input letter or it doesn't read an input letter, then it's allowed to do a test for 0. Is counter 1 0, is counter 2 0, and depending on whether or not, depending on which counters are 0, it's allowed to increment one of them and decrement one of them. Okay? And then Minsky machines are Turing complete. So you can write so the halting problem for Turing machines, for Minsky machines, or Minsky machine and two counter machine is the same thing. The halting problem for these machines is undecidable. So a halting problem means given one configuration and another configuration is there a run of the Turing of the Minsky machine which goes from here to there. Okay? So now you can see here that this is exactly the type of thing you can do. So you could have states. Maybe you could take, for example, PQR. For some, finite set PQR, 0, 2 states. You can extend this a little bit to take care of the states. Actually, the states are not even needed for the undecidability if you do it properly. And then the question, given in this specific graph, given one vertex and another vertex, is there a path from this vertex to that other vertex becomes undecidable. And using this idea, connectivity becomes undecidable. Okay? So that's why this doesn't necessarily need to be a decidable problem. But as I said, in the good structures, it is going to be a decidable problem. Okay? So now let me give you an example, and this is already, so graph reachability is undecidable. Sometimes it means, for example, graph reachability is the same problem as emptiness for finite automata. So, for example, emptiness for finite non-deterministic or deterministic finite automata is going to be an undecidable problem if you choose your atoms the wrong way. So these atoms. Okay? But if you choose them the right way, then it's going to be decidable, and I hope that this example here convinces you now that it's not at all clear why certain assumptions will lead to decidability. And now I will explain to you these certain assumptions, and I guess we'll take a break then, because I think it's a good moment to stop. Let me go here. I'll put this example. So the question is going to be this. For which choices of O is the theory going to work well? So, for example, is graph connectivity decidable? It turns out, by the way, that for the same choices of A where graph connectivity is decidable, I don't know, emptiness for context-free grammars, for minimization of automata, many usual decision problems are decidable. So it's not really connected to graph connectivity, it's just a fundamental property. And well, the answer is this. Oligomorphic. Okay. Well, I'm not sure how helpful that is, because for all we know, this could just be a name for those structures when it's decidable. But no, it's an actual standalone notion, and it can be defined it has several different definitions, and this is what I will explain now, and this will be the end of this lecture. Okay? So, what is an oligomorphic structure? It's a property of a structure. And these will be oligomorphic, these will not. Okay? So, the key notion is automorphism. So, an automorphism of a structure, it's a bijection of its universe. So it's a permutation of the universe, okay, which respects all of the relations and functions, which is an isomorphism of the structure with itself. So who does not know what an isomorphism for structures is? Okay, so we all know, good, but I will just remind you, for example, if there's a relation, and these are elements of the structure, then this is if and only if pi. So that's what it means to be an isomorphism. So you take a relation, you rename all elements, and then the relation still holds, or still doesn't hold. Okay? And it's the same for functions. So you can either say that a function is a special case of a relation, so this is a binary function from A to B output C, and then just apply this thing. Or the other way to do it is the usual way. If you have a function, then you can either first apply the automorphism to the argument and then apply the function, or you can first apply the function and automorphism to the output, and you get the same result. So that's what automorphism is. But so this is generally an isomorphism, but an automorphism is an isomorphism of the structure of itself. And oligomorphism will be defined in terms of automorphism. But let's first have a look at what are automorphisms in these structures. So what is an automorphism of this structure? Yeah, just only permutation of the universe, because all you need to do is preserve equality. And well, you have no choice, because if it's a permutation, then you will preserve equality. Okay? So we don't know what the random graph is. What's an automorphism of this? We'll give you an example. Translation. So x goes to x plus 2 will be an example. X goes to 2x. You can also square, yeah? Well, for the negative numbers, you have to negative square, yeah? If, generally speaking, any order-preserving function, it doesn't have to be linear or a polynomial or anything. And when I say order-preserving function, I'm just literally repeating the definition of an automorphism, because it's any function which preserves the order. Okay, so that's not really very helpful. Okay. Let's get arithmetic. What's an automorphism here?
Translation, for example?
No. Because 0 is special. In fact, an automorphism, because 0 is a neutral element, and any automorphism will need to map a neutral element to another neutral element. And there's just one neutral element, namely 0, so it needs to map 0 to 0. It also needs to preserve the order, so there's no automorphisms except the trivial identity. Okay? What is an automorphism of this? No, because you can identify the positive numbers as the squares, or well, sums of 3 squares or something. Like every number is a sum of 3 squares, every positive number, or 4 squares. So there's no automorphisms here. Again, except for the trivial one. What about here? So if you think about it, then it's all about prime numbers. Because every number is just, 2 to the power, every number is something like 2 to the power of 3 times 5 to the power of 8. And then what you do is you just do coordinate-wise addition of the exponents. So if you swap the prime number 2 with the prime number 3, then this is going to be an automorphism, yes? Understood in the appropriate way. So there are some automorphisms. And it's a general theme in logic, well, in mathematics in general, that a structure is properly described. You don't need to say what the structure, you don't need to give the relations and stuff. All you need to say is what are the automorphisms. One could go on about this for some time, but this is not going to be important. But generally speaking, the automorphism of a structure described it very well. Okay, so we had some examples here. So this is what is an automorphism. And then we now define what oligomorphic structure is that A has finitely many elements up to automorphisms. Which means, this is not I'm not done with the definition, okay? But what I've written so far means is that if you identify 2 elements by saying these 2 elements are similar because there's an automorphism which takes one to the other, it's also known as orbits, which is why you see the word orbit here, then there's finitely many orbits. Okay? So, how many orbits do we have in Skolem arithmetic? Okay, maybe how many orbits do we have in Pressburg arithmetic?
Infinity many.
Yeah, because there's only trivial automorphism. So every orbit has just one element. Okay? How many orbits do we have here? One. Because you can take every element to every other element. How many orbits do we have? Well, we don't know. How many orbits do we have here? One. Because you can take every about translations for example. Okay? Here we also have infinitely many because it's. But let me give you one more example so that it's. A column is a little bit more challenging. But if you think about it, 2 to the power of 3 and 5 to the power of 3 are going to be in the same orbit because you can swap 2 with 5. But 2 to the power of 3 and 2 to the power of 4 are going to be in different orbits. Because you can, if you think about it, the prime numbers are sent to the prime numbers, the squares of prime numbers are sent to the squares of prime numbers, and so on. So if you're the nth power of a there's an orbit called the nth powers of prime numbers. The 10th powers of prime numbers is an orbit. But there's infinite many powers you could have. So there's. But here's another one which is interesting. The integers with order only, and it's outside the zone of good things. How many orbits? What are the automorphisms here? Just move everything. Yeah? You cannot shift, you cannot expand things, so just translations and only translations. So the automorphisms group is the group of translations, so it's isomorphic to the additive group of the integers. And how many elements does it have? How many orbits does it have? One. So it may be oligomorphic. No, but it's not. Well, it's outside the group, so cannot be. Because the definition of oligomorphism, I'll make them into parentheses, it says that this is true not just for A, but also for A squared, and also for A third, and so on. So for every power, so there's up to automorphisms, there's finitely many elements. Up to automorphism, there's finitely many pairs of elements. Of course, the number of pairs of elements up to automorphism is bigger than the number of elements. Yes? As this power grows, the finitely many also grows, but it has to be always finite. Okay? So this one, it satisfies the first condition, but it doesn't satisfy the second condition. Because if you think about it, if you take 2 integers and you map them through a translation, then their distance is the same. So the distance of 2 integers is an invariant with respect to automorphism, and you can choose the distance to be anything. So, well, there's infinitely many choices of distance. And then, of course, you can come up with structures such that here it's finitely many orbits, here it's finitely many orbits, but when you take the third power, it's infinitely many orbits. But you can imagine it. So this finishes the notion of oligomorphism. And now is a good time. Okay, so it's going to work out in the end. It will turn out that if your structure is oligomorphic, then these things behave particularly well. Okay? In particular, this problem is going to be decidable, and it's almost if and only if. So it's like a very strong distinction. But let me make some comments about. No, I won't make any comments about this. Let's just see, is it clear that these two structures are oligomorphic? How many, say, triples of rational numbers are there up to automorphisms? How many pairs? Okay. Well, there's this pair. There's this pair, and there's this pair. And that's it. Okay? And generally speaking, it's sort of n factorial, but a little bit more because you can have things which are equal to each other. Okay? So this is oligomorphic. This is even more oligomorphic because there's more automorphisms, so there's less structure, so it's easier to be similar. So it's also oligomorphic. And as it will turn out, the random graph is also oligomorphic. And so for those of you who know the random graph, how many orbits does it have in the first power? Sorry? One. Because in the random graph you can take any vertex to any other vertex and this extends out. How many orbits does it have in the second power? Which is what? How many orbits does it have in the third power? Sorry? No. It's going to be, okay, I don't know. Generally speaking, in the random graph, if you have 3 vertices, x, no, it's going to be 8. Then they may or may not be connected by edges. And if you want to map this to some other triple x, y, z, then you need to have the edges in the same places, and that's enough. And if we're talking about the simple random, apologies to those who don't know this notion, we'll do it at some point, then you just have to, for each edge, you have to say what it is. Okay, so this sums up this part of the lecture. So what we're going to do, well, in the exercise session, I think we'll just get some experience with the set builder expressions and with oligomorphic atoms. And my goal for the next lecture is to explain why, under the assumption that the atoms are oligomorphic, these set builder expressions define a very well-behaved notion of finite sets. And in particular, there will be this other equivalent notion of orbit finiteness that I will discuss. That is going to be tomorrow. And in the second set of 2 lectures, I will try to put these abstract definitions to work on the specific example of Turing machines which test vectors for linear independence, and see what we can prove with that. Okay, so that's it for the lecture, and please feel free to ask questions. Okay, well then, if not, let's have a break. Thank you.
Nagrywasz?
Nagrywam.
Dobra, teraz mówię, raz, dwa, trzy, mówię w miarę głośno. I zobaczymy teraz.
So a set builder expression represents a set of sets of sets of sets. But sometimes it's just a set of atoms. So, yeah. So here's my question to you. Assume that the atoms have equality on. Which subsets can you define using the set builder expression?
All recurrent subsets.
Sorry?
Recurrent subsets.
What do you mean by that?
There is a Turing machine that decides whatever.
So, for example, can you do this for the even numbers?
I don't really think so.
Why not? We'll get it, sorry.
Because there's no first order formula that can define what is even number.
That is going to be the answer. But that will require proof. So let's start maybe with the counter-positive approach, you said. Suppose that you have a first order formula which inputs an atom and says yes or no. and it uses only equality, well, it's allowed to use constants. See, remember here, for example, you're allowed to use any specific value. I mean, every expression is finite, so you can't use finitely many values, but you're allowed to use it. So, what property, what subsets of atoms can you define this way?
Finite.
Yes. X is equal to 2 or equals to 8.
And cofinite.
X is not equal to 2 and X is not equal to 5. Okay, good. Anything else?
Well, so you can take some of, no, it's the same set.
So it doesn't look likely that you can define this. Yeah? But what's an argument? And I mean, there's different arguments that could be used to justify this, but I want to hear one, which uses the word automorph. Okay? So let me just start it. Suppose that you could define this set by a formula like this, where the constants used are 3, 7, and 9. Because it's a finite formula, so necessarily can only use finite many numbers explicitly. Imagine you could define this set by a formula with one free variable. It can be huge. You can, for further logic, quantify other stuff. But it's only allowed to use 3, 7, and 9. Or maybe, imagine it doesn't use any constants at all. This would be a simpler version of that. Because, I mean, why would it be useful to write 7 in the formula? Yeah? So, imagine I could define this set by a formula which uses only equality and doesn't use any constants at all. What goes wrong and uses the word automorphism?
So if this formula is true for this set, then it's also said true for every image of this automorphism.
Under any automorphism. Right?
Under, yes.
So imagine you take some automorphism pi, which in the context of equality only it just means bijection of the set itself. And if some x satisfies the formula, and then you map that x via pi to some other pi of x, then pi of x will also satisfy the formula. Because first order logic is invariant under automorphism. This is not so hard to, I mean, this is a fundamental fact. So let me write this as a fundamental fact. Okay, let me just write that A be a structure and take some formula phi x1 xn, which uses the vocabulary of the structure. So if the structure has equality only, it uses equality only. If the structure has order, then it's allowed to use order. So over phi. Over n is allowed to use the vocabulary without constants. Then, for every element of the structure, and for every automorphism, apply an automorphism to something, this will not change the validity of first order logic. You just prove this by induction inside the formula. There's nothing really to do. Okay? By the way, this is a philosophical fact. So, for example, some people, including Tarski, who sort of invented first order logic, one of them called them, he said that logic, and what does it mean to, what's a logic? It's a device of identifying properties which is isomorphism invariant. So that's what a logic is. You find anything that's isomorphism invariant, that's going to be a logic. In this wider sense. Okay, that's the paper. What is a logical notion? That's the answer. Anything that's isomorphism. Okay, that's more general notions. And if you take anything that are known as logics, like first order logic, second order logic, I don't know, eighth order logic, they have this property. So this is sort of like by definition of being a logic. Of course, if you view logic in a reductionist way as it's quantifiers, then it's just you have to prove it, but it's sort of foundational. So from this fact, it follows that if you could define this set by first order formula without any constants, then the set would be closed under automorphisms. Okay? Well, so what kind of sets can you define by a first order formula without constants? What kind of subsets of A can you define by formulas without constants? How many subsets?
Two.
Beneath our dignity to say which ones. So now let's take a slightly stronger version of it, which is kind of clear. If it's with constants, say it uses constants C1, C10, it's actually the same result except for a different structure. So a formula with constants can be viewed as a formula without constants in a structure where the constants are just added to it. So there's no difference here. So if you add this, then it's true, but now you have to strengthen the assumption so that you only care about automorphisms which do what?
Preserve constants.
Preserve it. But this is the same result as the blue one, it's just what's a constant. So how many, okay, now which subsets of the atoms can you define by a formula that uses constant 1? It's allowed to use constant 1. So which kind of subsets of the atoms can you define? Give me some of the subsets. I think there's 5 of them. 4, I think. So which subsets of the atoms can you define by first order formula that just is allowed to use 1, but not allowed to use 2? Okay, yeah. So you're allowed to. You have to give an answer to is 1 okay? And an independent answer to the question is not 1 okay. And 2 and 3 are okay. And I'm sort of trying to condition you to get used to these automorphisms. This is the point of the exercise, because let's view this in terms of automorphisms. If I look at the atoms and I consider orbits, these are the atoms with equality on them, okay? And I consider the orbit with respect to arbitrary automorphisms. How many orbits are there? There's just one orbit, because everything, you can map 2, 3. If, however, I require them to be the identity on atom 1, then there's 2 orbits. There's the orbit which is 1. And there's the remaining orbit which is not 1. And this result here says that if you're a subset of the atoms, which is defined using the constant 1, then if you're true for somebody here, you're true for everybody else. So you either take this entire orbit or you don't take it. And then you either take this entire orbit or you don't take it, which means that there's 4 subsets, depending on which one of these you take. Okay? For each one of these you take. So in general, if you are allowed to use constants 1, 2, 3, 4, 5, then there's going to be 6 orbits, namely 1, 2, 3, up to 5, and then generic. So there's going to be 64 different subsets that you could. Okay. Now, and in particular, all of them are going to be finite or cofinite, as we have argued before. Yes? So that gives an answer. It can only be the finite and cofinite set. Here's another observation, which will also play a role later on in the lecture. Do we have, for this particular structure, do we have anything to gain by using first order logic, namely quantifiers? So suppose I want to define a subset of the atoms by a formula of first order logic. And is it useful to have quantifiers here? No, because that's what we just argued. If the formula uses constants 1, 2, 3, 4, then it's only allowed to compare its input with respect to equality to 1, 2, 3, 4, so it could do that without quantifiers anyway. So in fact, this structure here has something that's called quantifier elimination, which means every first order formula is equivalent to one that doesn't use quantifiers. That will play a role later on in the theory. It will turn out that the structures, well, for the oligomorphic will be a slightly stronger property, but it will imply quantifier. So now let's consider the following question. Which binary relations can be defined, and just to make it simpler, without constants? So, in other words, this should have been proved. We didn't really prove it, but that turns out, what can you define using a formula with 2 variables? So give me 2 examples of such binary. Okay, 3. Sorry?
X equal y, for instance.
X equal y. True, false.
X not equal y.
Anything else? Why not? So every formula, as we have here, is going to be invariant under automorphisms. So how many pairs, so if it's going to say yes here, then it's also going to say yes to I1 of I2. So up to atom automorphisms, how many pairs are there? 2. Equal or not equal? Okay? So a formula, you just have to say, what does it say here? And what does it say here? Yeah. And there's 4 kinds of things you could say, and these lead to these 4 formulas. That's everything you can do if you're not allowed to use constants. Okay. If you're allowed to use constants, then it's a little bit more fancy, but there's nothing really going on. So you can make exceptions, you know. If the first coordinate is equal to 2, then something. Okay. So now, this is a straightforward consequence of what we have just discussed. Which functions can be defined by a set builder expression without constants. Identity. What else? That's it. Because a function is a binary relation, and we just listed all binary relations, and only one of them was a function named identity. So, what about if you're allowed to use constant 1? How many? This should be like 3 or 4. So identity is still okay. What else? So x is the first function, the identity. The other one is everybody goes to 1. Another one?
Nothing goes to 1. Okay.
That's not possible actually. Because if you get 1 as your input, and your output is meant to be defined in terms of your input and 1, there's nothing you can do. So, but what's an example?
Is equal to 1.
Well, actually, you're right. I think that's it. Because in general, you could imagine a function which goes like x goes to something if x equals 1, and something else if x not equals to 1. This is the general type of function you could imagine. Right? Unfortunately, in this particular case, if it's equal to 1, you have to write 1, because what else can you write? X, that's not a number. And then here you can either write x or 1, and neither basically only these two. But then you can imagine, like, if you have, say, if you're allowed to use constants 1 and 2, then you can go a little bit beyond this. Yes, you can say, like, you swap 1 and 2, and for the other things, you're the identity and stuff like that. Okay. Okay. So now, here's an example which actually goes back to like 100 years. Which is this? The family of unordered pairs. Okay? Clearly a set builder expression. So it's set right out, right? So is there a choice function? Can you write a set builder expression which describes a function that inputs an unordered pairs and gives you one of the elements? This is what I mean by a choice function. Is it clear what a choice function is? such a choice function? Who thinks that there is? So who thinks that there isn't? Are you thinking two things at once? Who knows, maybe. It depends on the axioms of set theory or something. Once you start using words like choice function, well, the natural answer, and as witnessed by your vote, is no. But the issue is, how do we justify this? So, let's first answer a simpler question. Is there a choice function such that the definition does not use any constants? I mean, why would it be useful to write 5 in a choice, in the definition of a choice function? That would be a little bit useful, because if your input set contains 5, then you can always output 5, yes? But that doesn't go a long way as a solution. So why is there no choice function in this discipline? I mean, described by a set builder expression.
You can consider automorphism swaps x and y. And
Exactly. So imagine you had a choice function, and your input was, say, 3, 2. Okay? And then this choice function says 3. Just about this. Okay? Now consider the automorphism pi, which just swaps 3 and 2. Okay? Then, intuitively speaking, we will justify this in a moment more pedantically, but intuitively speaking, if you apply the automorphism to the input and you apply the same automorphism to the output, it should be consistent with the choice function. But if you apply pi to the input, what happens to the input? Nothing. What happens to the output? Something. So it will be a multivalued function, which means not a function. So that's the idea. And now let's generalize this argument. Can you have a choice function that uses constants 1, 2, 3, 4, 5, 6, 7? It's for the same reason, but except for 3 and 2, we would use 103 and 102. Same argument. Okay? Well, we will formalize this in a moment. No, it's not very hard. But what it says is that if your notion of functions or your notion of sets is the one that we're using here, so they're definable in this particular discipline, then the axiom of choice fails.
Can you define any function for this set? Like,
No.
what's the signature?
Well, you can. You can define a function which takes everybody to 3
So we need a constant.
with constants.
Yes.
Without constants, you cannot define any function. With constants, you can take everybody to 3. Or, everybody to 3 with finitely many exceptions, which can go to 7. So you see, we're dealing with, you're not allowed to do all kinds of operations. So clearly, I mean, since they're defined by logic, then clearly there's some things you cannot do because there's countably many things you cannot do. But there's even quite natural things you cannot do. Okay, and this failure of choice is going to be an issue. Okay, it's going to be an issue in some places. I mean, one place is going to be determinizing Turing machines. You can imagine that many natural procedures are going to go choose an element of the input set, and then you're not allowed to do that. So, what you going to do? So let's formalize this argument. Not very much. Just so that you can see what's happening. It's a version of the blue thing, so maybe I write it together with the blue thing. So suppose you have such a function. So suppose you have a hypothetical choice function, but we call it a function, but formally speaking is a set. Yes? It's a set of pairs of sets and elements. Yes? So now you can show that if x, so let me call it x, take any set defined by a set builder expression which uses constants C1 and Cn. Then an element belongs to x if and only if where pi it's the same reasoning. Now we have to be careful what this means, because the little x is not necessarily an atom. Yes, it could be like a pair of atoms or a set of pairs and so on. So but it's a natural lifting. Yes, so we just apply it to the whole thing. Is it clear what I mean by pi of x, where x is now possibly a set of atoms or a set of pairs of atoms and so on? We just apply it everywhere. Okay. So that means that if you can define anything using these constants, then that anything is going to be invariant under applying automorphisms which preserve those constants. So if you apply this principle to the choice function, then you get exactly the argument that we have. Yes? Because now we say I take a hypothetical choice function, then formally speaking, this means that the pair 3, 2, 3 is in the function. And then if you apply that automorphism, which is equal to 2, 3, 2, then that will also be in the function. And this is, of course, equal to 3. I don't know why I wrote 3 in the wrong order. So this is a principle, and there's even a name for this. This thing here is called C supports X. So C supports big X means that if I take an automorphism which doesn't touch this, then it doesn't touch this. Okay, so let's write this out in it's going to be an equivalent statement, but it maybe might be a little bit more clear why it's called. So that if pi of x equals x, then pi of c x. Yeah, because pi of x equals x is this thing, which is written out in a slightly different way. So that's a notion of something supporting something else. Let me maybe write it in yet another way. Which is the following. I take two automorphisms. So why is this equivalent to this? It's a question. So which implication is obvious? bottom to up because you can take sigma to be the identity. Yeah? So from top to bottom.
Can you compose the one isomorphism with the inverse of the other and apply it to both sides?
So I want to apply something to both sides here. What? Sorry, so what do I apply?
So you take pi composed with inverse of sigma and use it as pi in the above equation, or the other way around.
We want to, knowing this, we want to prove this. Yes? So let's apply sigma inverse to both sides here. But this is this. So now using this implies using symbol star. And now I can reapply sigma. So I did use some implicit. Did I make a mistake somewhere? So I made some assumptions here. Let's try to see what was really said here. So what we have is we have a space where the elements are C bar or maybe big X. This space consists of all things that I can construct using atoms. Maybe tuples of atoms, sets, and so on. On this space, so we have a space like things constructed using atoms. Let me be vague about what that means. And then on this space, there is an action of the automorphism group of it. So for every pi, you can apply it. If you take a pi here, and you take an x here, then you can apply pi to x and get a new thing constructed with atoms. Yes, that's what's happening here. So what are the assumptions used to make this this argument work? Well, it's called, these assumptions are that it's a group action. So let me explain for a moment. So first of all, I assume that there's this expression here can be understood in two ways. The first one is, I first apply pi to C and I get something, and then to that something I apply sigma minus 1, and then I get a new something. The other way I can understand this is I first compose these things and then I apply it. And then this you call it, here actually I use both perspectives, so it's important that it doesn't matter. That's what being an action is called. And then the other thing, which is a corollary of that, is that the, well, it's not a corollary, is that the identity does not do anything with it, doesn't move things. And then, all that works. So, this notion of something supporting something else, it's actually just, this is just for general culture that I say this. Notion of A supports B, it's a notion that lives when A and B are equipped with an action of a group, and then it just says that any element of the group, if I want to know if any element of a group which fixes A, it also fixes B. Or equivalently, if I want to know the group action on B is uniquely determined by the group action on A. And this will play a role later on in this unit. So let me ask another question. Is there a total order and by a total order I mean a total order defined by a set builder expression. Yes or no? Here you should quickly give me the answer.
No.
So why not?
Can you distinguish the definition?
So suppose that this total order would say 1 is smaller than 2. And this total order would not use constants 1 and 2. And you can swap 1 and 2 and blah. And this Vincent gave another argument, is that if there was a total order, then there could be a choice function which would say this minimum. So that's another argument. What about this one? Let's change the atoms. Okay, so is there a total order on atoms? With the way I see that you understand it is that you're saying, oh, that's fun. That means good, because it's supposed to be stupid. Is there a choice function?
Yes.
Minimum. Okay. Is there a well-founded order of the atoms? Why not? So is there a well-founded order? You can see that these constants, they typically play no role. So let's just ask, is there a well-founded order that is defined without constants?
With minimum conditions, yes. There was well-founded order, then there would be a minimum.
There would be a smallest element, yes.
So, yes, can be shifted.
Yes, that's correct. So here's a way of formalizing. I mean, I'm not sure if it's the same thing. So if you have a well-founded order, then you have, as you said, you have a smallest element. If you could define the first order, the order with first order logic without using constants, then you could also define the smallest element with first order logic without using constants, the smallest element of this particular order. And can you write a formula phi of x here of first order logic which selects exactly one element? No, for exactly the same reasons as before, because they're all in the same orbit. So if it's true for 5, it's also true for 3. Okay? So is this what you meant, Victor? Yeah. So there is no well-founded order. So maybe a little bit of historical perspective. The idea to use things like this, it dates back to Abraham Fraenkel. I think in the 1920s. And well, this choice, of course, it was inset here, so he used words like choice. And what happened? He said the following thing. I mean, at that point, we didn't know if the axiom of choice is provable or not. Now we know it's not provable. Neither is it disprovable, it's independent. But at that point, Who knows? I mean, maybe you could prove the axiom of choice, maybe you could. So what Frenkel did is he constructed a model of set theory where the axiom of choice is not true. And that model was, you're not allowed to construct all sets. It's not exactly what he did, but for the purpose of this conversation, it's good enough. But you're only allowed to construct these set builder expressions. Okay? And to be more formal, what he did, and it's almost it's closely related, is he said, let's consider the following thing. You're allowed to consider sets. There's these atoms at the end, but not all sets are okay. You're only allowed to have sets which have a finite support. So those sets for which there exists some finite tuple C which satisfies this. So that's what Frenkel said. Let's consider only the finitely supported sets. Again, because sets are hierarchical, so it's actually not only is the set finitely supported, but every element is finitely supported, and its elements are finitely supported. So he said, let's consider these sets. And then he shows it's a model of set theory. Okay? But it violates the axiom of choice. Because you cannot have a finitely supported choice function. So that's what he said. Now, clearly I'm lying to you, because otherwise he would have proved that the axiom of choice does not follow from set theory, which was proved only in the 1960s. So what he actually showed is that he didn't show it's a model of set theory, he showed it's a model of set theory with slightly different axioms. Okay, but these were reasonable axioms, okay? So that's what he did. So this is the historical origin of these ideas of considering support, and the choice was there at the beginning. And then this stuff continued for some time. This was picked up by our man Mostowski, Andrzej Mostowski, in the 40s. And he did some interesting work there as well. He considered stuff with orders and stuff like that. And so today, these sets with finite support, they're called Frenkel-Mostowski sets. But this doesn't fully capture what we're talking about here. It's not really the same topic, because we are interested in things which are finite and finitely representable and so on. That's not the topic there, and the topic here is always finite. Okay, so let me maybe take 5 more minutes. So maybe one last thing. I think this might end up I'm sorry. I think it's a good place to stop. So what we're going to do tomorrow is we are going to give an alternative description of these set-builder expressions, which does not use any syntax. It doesn't say anything that can be defined by expressions of this shape. It's going to be based on automorphism. And there will be some advantages of that. Well, you already saw the advantages of working with automorphism, because we didn't, in order for all of these were very straightforward negative proofs. And we didn't need to go bother with the syntax. We didn't need to say, if the expression has this shape, then blah, blah, blah. If the expression has some other shape, blah, blah. That would be incredibly tedious. So this is a nice thing about having this group theoretic approach to it, which will continue to be a profit for us. So that's the plan for tomorrow. We're going to have a semantic perspective on these set-builder expressions, which is going to be defined purely in terms of automorphism, what you can do. So that's question. Sorry. Sorry.